Okay, so in this video, we will find the volume of a solid using the idea of infinitesimal cross sections. So let us first consider the following region bounded by the curves y equals x squared and y equals 4x minus x squared. This is a parabola facing upward. This is a parabola facing downward. Let us first find the points of intersection, so we equate both y values. Send every term here onto the left-hand side, and you'll get 2x squared minus 4x is equal to 0. You can factor 2x. Another solution is trivial. Either x is 0 or x minus 2 is 0, in which case x is 2. We want the points of intersection, so we want both the x and the y coordinates. So x is 0 in the first case, x is 2 in the second case. And now, to find the corresponding y value, we can use either curve, as we have found points of intersection. So these points lie on both curves. So we take the simplest curve, x squared. If you square 0, you get 0. If you square 2, you get 4. If you notice, both points have positive coordinates, so our region will focus in the first quadrant of the xy plane. So let's sketch the region. Y equals x squared. And the inverted parabola, 4x minus x squared. The point 0, 0 is the origin. The point 2, 4 will be somewhere here. So there you go. You can clearly see that the region bounded by these two curves is the following region, which lies exclusively in the first quadrant of the xy plane. This is the curve y equals x squared, and this is the curve y equals 4x minus x squared. And our points of intersection again is the origin and this point where x equals 2 and y equals 4. Okay, so now that we have this region, how can we use it to construct a solid? The idea is, think of this region as the base of your solid, and onto this base we will erect a particular solid, and we'll think of here in this case erecting infinitesimal squares. So imagine that this is the base again of your solid. So imagine erecting, setting up onto this base, this region, one infinitesimal rectangles that are perpendicular to the region, therefore to the xy plane, and also perpendicular to the x-axis. So you imagine setting up onto this region an infinitesimal square. And we can take any cross-section that we want. Here we choose to take a square. It is positioned along the x-axis. So imagine standing on this region at this particular x value, an infinitesimal square perpendicular to the base of the solid, so it's standing up straight, and perpendicular to the x-axis. So let me draw our three-dimensional infinitesimal square. So imagine taking this infinitesimal square and so picking it up and placing it on top of the region so that it is one perpendicular to the region and also perpendicular to the x-axis. And you can construct now a complete solid if you place these infinitesimal squares all over the region. This will generate a very complicated solid, which I will not attempt to draw, but you can imagine as you set up these little infinitesimal squares all over the region, then you'll get a solid. And we're going to ask, well, what is the volume of this solid? Well, let us first find the volume of an infinitesimal cross-section, which is an infinitesimal square. Well, let's find the thickness of our square, which is the width of the rectangle. The base of your square is this rectangle. You're placing the square where the base here lies on top of this rectangle. So, the thickness of the square, is the width of the rectangle. The width here is an infinitesimal change in the x-axis, so of course it is given by dx. Well, the length of the base of your square is the length of the rectangle. This is a segment along the y-axis, so we need the larger y value, 4x minus x squared, and the smaller y value, which is x squared. Therefore, the length of this rectangle is obtained by taking the larger y value let me put it here. So the height of our rectangle is the larger y value, 4x minus x squared, minus the smaller y value, which is of course x squared. And if you subtract, you of course obtain 4x minus 2x squared. And we can factor from this a 2x. So factored, we get 2x times 2 minus x. 2x times 2, 4x. 2x times negative x, negative 2x squared. So we now have the length of the base of our square, 2x times 2 minus x. But again, as we are erecting squares, the height is also the same, 2x times 2 minus x. And if you think of it, it is quite easy to find the volume of this infinitesimal square, this infinitesimal cross-section of our solid. The volume is quite simply the area of the square surface times the thickness, dx. So it's this times itself, therefore this squared times dx. If we distribute the square on all three terms, we get 4x squared 2 minus x all squared dx. So now we have the volume of an infinitesimal cross-section of our solid, and you can ask, well, how do we then obtain the total volume of our solid? Well, of course, it will be by summing. Now we'll use uppercase V for the total volume of the solid, and we can obtain this volume by summing, which is integrating, the volume of every little cross-section of our solid. The volume of those cross-sections is 4x squared times 2 minus x all squared dx. And we're summing with respect to x, and the cross-sections will begin here when x is 0. And then we'll go all the way up to here where x is 2. So by summing the volume of all the little cross-sections, these infinitesimal squares, over the full range of x values of our region, we will obtain the total volume of this solid. And now it's just a matter of evaluating this definite integral. First step, we factor out the 4, as it is a constant multiple. Second step, if we leave the square here, we can't integrate, so we'll square this. So x squared times 4 minus 4x plus x squared. We still can't integrate as we have a product between two functions of x. If we multiply, then we'll be good to go. So it's 4x squared minus 4x cubed plus x to the 4. And now we can evaluate this definite integral using, of course, the fundamental theorem of calculus, finding our antiderivative, which is trivial here, power rule on each term, which gives us 4 times 4x cubed over 3, so 4/3 x cubed, minus 4x to the 4 over 4, the 4 over 4 cancels and leaves us with x to the 4, plus x to the 5 over 5. And we evaluate our antiderivative from 0 to 2. If you notice though, there's a common multiple of x cubed, so let's factor this out. So we have 4x cubed times 4/3 minus x plus x squared over 5 from 0 to 2. So we evaluate the antiderivative at 2. So 4 times 2 cubed is 4 times 8. 4 over 3 minus 2 plus 4 over 5 minus the antiderivative at 0. But if you notice, if you replace x by 0, you get nothing. So here's the end result. Let us now simplify into a single fraction. 4 times 8 is 32. We'll put every term over 15. So 5 over 5 will give you 20 over 15, minus 15 over 15, 30 over 15, times 3 over 3, 12 over 15. Well, 20 minus 30 is negative 10, plus 12 is 2, so it's just 2 over 15. And 32 times 2, of course, is 64. So the volume of our solid is 64 over 15 units cubed. And that's it. So if you go back to the problem, these two curves bounded a region in the xy plane. We thought of the region as being the base of our solid, and onto this base we erected infinitesimal squares that were 1 perpendicular to the base of our solid, the region in the xy plane, and also perpendicular to the x-axis. We found the volume of an infinitesimal square, an infinitesimal cross-section of our solid, and by summing up over the entire region the volume of every infinitesimal cross-section, we obtain the total volume of our solid, which is again 64 over 15 units cubed. And that's it.